All right, so I wanted to make a lesson that we kind of summarize how we analyze resistor circuits by combining both KCL and KVL along with the parallel and series resistors, okay? So just kind of outline what are the steps when we are solving circuits with resistors here. So first step is, this is optional. You might combine any parallel and series resistors. That's only if you do not need to analyze the separate components, okay? So it's up to you on this one. This is an optional portion. Depends on the problem whether you're going to do this or not. Okay, number 2, we're going to draw the direction of the current for every device. So every voltage source, every resistor. Usually we're going to have the current come from the battery voltage source and loop around, okay? That's the general path. Now, if you can't tell for sure, and that's mostly because there may be multiple batteries or things like that, then just make a guess. What will happen if you work out the math and you guess wrong, then what's going to happen is that you're going to get a negative answer for the current, and that just means you just simply guessed that the direction was incorrect. But just assign an arrow. I would literally draw an arrow on the circuit diagram for every component which way you think the current is going. You then want to draw positive and negative signs across every device. For batteries, the longer edge thing is the positive side and the other side is the negative. And then for every resistor or capacitor or any other component, the current always goes from the positive terminal to the negative terminal. So what that means is you always put the positive side, and you're annotating it on the circuit. The positive side is always the direction the current is going into. And then for every resistor, if you know two values of V, I, or R, then use V equals IR to solve for the third quantity. And then we apply KCL and KVL to solve the voltage and current of every component in the circuit. And that's what we're going to do. So let's go through a few examples of kind of how this operates. Okay, so for example here, in the circuit above, what is the value of the potential difference between points X and Y if the 6-volt battery has no internal resistance? So here's an example. We're going to draw the current, and I'm going to draw the current in red and say the current, this is going to come out of the battery here. This is going to be my I. It's going to flow this way, and then it's going to split between two branches over here. Okay, so we'll call this I1, and then by KCL, I1's going to go here, and then these two, the I1 comes in here, and then it splits into two, I2 and I3, and it flows like that. We're just establishing directions. Now, you can switch the directions, but generally, it's going to go from positive to negative. That's the general of the current flow. Then we're going to assign the positive and negative directions on every device. So for the battery, it comes out of the positive. This is the positive side, and the current comes out of the battery. That's okay. But for every other device, you want to make the voltage positive and negative like this in the direction of the current. So the current's coming this way, so this side's positive, this side's negative, this side's positive, this side's negative. And that indicates the potential difference across each of those devices. Okay, and what we want the value of the potential difference. So we want to know what this part here is. Now, the thing is we don't know everything. So what can we do at this point to help you analyze? So the idea is, at this point, if I know 2 or 3 things combined, or 2 for every, like the resistor, and I don't know the voltage, I don't know the current. Same with this resistor, I don't know the voltage. So I need to know 2 quantities to solve for the third one. I don't know any of those things for this one here. So what can we do? Well, we could combine these two into a single resistor. So this is the optional part of combining resistors. So you can combine it. I'm going to show you that way to do it. And if you don't want to combine it, I'll show you the other way to do it. Now, 2 resistors, because they have the same potential across them, because they're connected on the top and bottom, they share connections there. That makes them parallel. Then you say 1 over R equivalent is 1 over 3 plus 1 over 6. And this is this is 1/2. So the R equivalent of these two is going to be 2 ohms. So then it's going to be, this is 4 ohm, this is 2 ohm. And we just simply say those 2 resistors are now combined. And then this is 6 volts. And then you can say these 2 resistors are now in series. So then this could be 6 volts. And then you could just say, well, there's a single resistor here of 6 ohms. And now you can say, okay, well, the current comes out here. It's the same as I1, because it's the current that's coming out of here is I1. And then the potential difference here is this voltage, and I1 then flows into here like this. And so you could say like, oh, well, I know this voltage drop. Why? Because it's shared with this one right here if I do my KVL, or you can just see here, this 6 volt, it's 6 volts here, which means this current is going to be V over R, which is 6 over 6 or 1 amp. So now what we know is 1 amp is coming out of here, which means this is 1 amp. which means now I know what the voltage drop here, because now for this resistor, I know the current, and so I times R is 4 volts. And now I know that this voltage drop this is up 6 volts, down 4 volts, and then down here it's going to drop, has to drop 2 volts. Why? Because if I go in this loop, I go up 6, I have to drop 6 volts by my KVL. So I know if this is a 4 volt drop, this is a 2 volt drop, and that answers that question right there. What is the potential difference from there to there? Is 2 volts, and those two are parallel. Okay, let's say you didn't want to let's say I didn't want to combine the series. Then the way we do it is we set up a bunch of equations like we did in the lesson on KVL and KCL instead. So then we say like, okay, I don't know I1. Okay, so then I would say like, well, I'm going to do a loop equation here based off of I1. And so I would say anytime you go from negative, like we start here and we're going to move around this loop like this. So you're going to say I go up 6 volts. I'm going to drop I1 times 4. And then I'm going to drop I2 times 3, right? Every IR I'm going to drop there, and that's going to have to equal 0. Okay? So what this does is it allows us to create an equation here with these variables. This is the KCL KVL technique that we could have done. But again, with that annotation here. Now, it would have been easier if you just kind of used this one, but it's fine. Like, you can do this. Then we'll maybe do another, or we do another loop maybe for this one right here. This one's a little bit interesting. You're going to go up this voltage and then down this voltage, right? Or another way to say it is the voltage across here, the voltage across the 3 ohm resistor equals the voltage across the 6 ohm resistor because they are parallel, right? Or you can do the KVL, and then that would be, how could we do the voltage in terms of the currents? That would just simply be I2 times 3, because that's the voltage across here, I2 times 3, is equal to the voltage across here, which is just I3 times 6. Right? And so then you can solve, you can say I2 is equal to, say, 2I3. And then this is going to allow you to solve, or actually, well, okay, that's one equation. So now we have, the only problem is we got I have, the way you want to think about this is I have, 2 unknowns, or 3 unknowns, only 2 equations. Last equation is going to be KCL. I say I1's coming in, I2 and I3 are leaving this part here. So I1's equal to I2 plus I3. But then you can plug I2 into here. Actually, we'll get rid of I3 because we know I3 is equal to 1/2 I2. So that goes into here. So that means I1's equal to I2 plus. You can see why the series parallel is a lot faster, right? So this is going to be 1/1 1/2 I2, and this is 1.5 I2, or 3/2 I2. Then you can replace I1 with that, so you're going to get 6 minus 3/2 I2 times 4 minus I2 times 3 equals 0. 4 times 3/2 is 6. 6, and then minus 3, that's going to be 6 minus 9 I2 is equal to 0. And then I2 is equal to 2/3. 2/3 amps. And then finally, to find the voltage across here, across the 3 ohm, is again the I2 times the 3 ohms there, which is 2/3 times 3, and that gives you 2 volts. Okay, see how much more complicated it is? That's why the combining of the series and the series and parallel resistors can get you. But you can get the same answer with a bunch of equations like that, okay? Let's look at another example, and we're going to use a series and parallel from here on out just in order to take advantage. So we want to know what the value of R is when the current is here. So again, we're going to start with drawing all the currents, right? So I have the current coming out here, and I know that this current has to match that current by KCL. There's nowhere for the current to go, so it's 0.5 amps. And then we might as well combine those into a single resistor, and those are parallel, right? Because they share, so it's 1 over R equivalent would equal 1 over R plus 1 over R with R, which is 2 over R. So the R equivalent is going to be R over 2. So then our circuit, so just replace it with a single resistor of R over 2, and then again we have the current going through there like that. And then we're going to sort of do our voltage drops always for the resistor. So for this guy, it's plus minus for the battery, like that. But for every resistor, it's going to be plus or minus. The current is going to flow from positive to the negative terminals, like that. Okay, and then we're saying like, okay, now this is the voltage drop. If you know I times R, or this one I know R, I know I, so I can solve for V. V equals IR. So 10 times 0.5 is going to be 5 volts there. And then here, I know that this is 0.5 amps, but I don't know what the voltage drop is, nor do I know R over 2. However, I can use KCL because I go up 10 volts. This is a drop of 5 volts. And if I go around this loop, I got to drop another 5 volts right here in order to get back to this 10 volts. Right, so go up 10, down 5, down 5. So now I know the voltage, and now I can relate the equation V equals IR. V equals IR. And we would say 5 is equal to 0.5 times R over 2. Okay, and so then R is going to equal 20 when we solve for R there, like that. Okay, let's look at this one. Circuit above diagram it has an internal resistance of 4 ohms connected to a 16 ohm and a 20 ohm resistor in series, and we have the 3 amps here. What is the EMF of the battery? What's the voltage of the battery? So again, let's draw our currents. Our currents are going to go like this, and this is 0.3 amps. Through this resistor is 0.3 amps, and then it's going to wrap around, and over here is going to be 0.3 amps. Okay, now we're going to annotate the positive minus, the positive minus, and the positive minus. Okay, remember for the resistors, the current has to flow from positive to negative. Now I times R, because I know the I and the R and the IR of these, I can find the voltage drops here. So what's I times R? That's going to be 4.8 volts. This is going to be 20 times 0.3, which is going to be 6 volts. This is going to be 4 times 0.3, which is going to be 1.2 volts. And then you do your KCL and you say whatever the voltage drop here across this battery has to equal all of these drops. So it's going to be 12 volts here. You're going to add them up. You're going to do 4.8 plus 6 plus 1.2. And that's doing KVL on that loop right there. Okay? So that's the idea. This is the basic strategy. Let's do a more complicated, longer, old FRQ problem. So in the circuit shown above, the circuit delivered by the 9 volt of internal resistance 1 ohm is 3 amps. The power dissipated in R2. Now they're using power. Power is I times V, so we know that I times V is equal to 12 watts. So we can use that if we know something about that thing. Determine the reading of the voltmeter in the diagram here. So let's draw our currents that are coming out. So we got 3 amps. So we have 3 amps coming out of here. It's going this way because they've already annotated the arrow. And then it splits into, say, I1 and I2 because these are 2 parallel branches. No current ever goes through the voltmeter. Otherwise, that would affect the circuit. And then they recombine over here. And then back in this branch, through here, we got to have the full 3 amps. Because this 3 amps has to travel from there to there. It's got to, by our KCL, all that current has to just continue in this path like this. So 3 amps comes in, goes through the battery, and 3 amps comes out. Right? That's KCL. There's nowhere else for the current to go. Now, we're going to annotate our positive and negatives. So this is positive and negative for the battery. Positive and negative because it goes from higher to lower, higher to lower, higher to lower like this. Now for this guy, I do know the voltage drop. The voltage drop, so I look at it, I just say like, well, from here to here, 3 times 1 is going to be 3 volts. Okay, and then this is 9 volts. But if I look at this loop, I go up 9 volts, I'm going to go down here and go down here from positive to negative, right? I have to drop 6 volts here because I got to go up 9. Then that's KVL, right? I go up 9, then I'm going to drop 6, drop 3, and that gets me back to 0 if I go through that loop. So these guys have to be 6 volt drop. And that is the voltage across here and here because they're parallel. They share a connection. So the voltage drop here, the voltage drop here, and the voltage drop here are all 6 volts. Determine the resistance of R2. Now, here, again, we know the voltage drop. We don't know the resistors, nor do we know the currents. However, we do know something about the power going through here. We know I times V is 12 watts, and we know the voltage. So that means we can solve for the current through this guy, right? So that's going to be I2 times 6 now is equal to 12, and so I2 has to be 2 amps. So that means now we know that this is 2 amps. Okay? Now I know the voltage and the current, how do I solve for the resistance? Well, V equals IR. So that means the 6 volt across here has to equal to the 2 amps through that resistor times R2. So R2 has to equal 3 ohms. How about R1? Well, let's take a look at this. Well, I know 3 amps is coming in, 2 amps is coming out, so I know that this one actually has to be 1 amp, right? Because it's a total of 3 amps. That's my KCL there. And so now I know the current and the voltage. I can then figure out the resistance. So I would say, again, V equals IR. I would say 6 is equal to 1 times R1. So R1 has to equal 6 ohms. All right, so that's the technique. That's how we're going to go about handling these kinds of cases and how we break down a circuit like this.